Taiwan, the beautiful island of Formosa, has seen maritime transport as a crucial conduit for international connections since the age of exploration, continually increasing the demand for ports and vessels, thus spurring the birth of the shipbuilding industry. From the design and structure of the ship, the use of engines, and various instruments, machinery, and electrical systems, all are essential components of shipbuilding, hence driving the development and advancement of technology. Since 1970, with rapid economic and trade development and intensified international exchanges, the demand for large vessels has been growing. Within the government's plan for the 10 major construction projects, 1/3 are related to ports and maritime transport. The China Shipbuilding Corporation, located in the Shaojiang District's Linhai Industrial Park of Kaohsiung City, was the first major project completed among the 10 major construction projects and was renamed CSBC Corporation of Taiwan in 2007, bearing multiple national tasks such as shipping, trade, national defense, and industrial development. The shipbuilding company's Kaohsiung main plant covers 93 hectares, originally Linhai fish ponds and sugarcane fields. This project was a joint venture between the RSEA engineering agency and the Japanese Kojima Corporation, aiming to build a million-tonnage dry dock. The dry dock, 13 meters below sea level, measures 950 meters in length, 92 meters in width, and 14 meters in depth, divided into 3 sections by 2 middle gates, each capable of independent operation. In January 1974, the RSEA mobilized a large number of experienced engineers to start a massive earth excavation operation. The main construction equipment for this task included a 28 cubic yard scraper, along with loaders and dump trucks for support. The site for the dry dock, nearly 1 kilometer in length, was divided into 2 development areas for excavation. The first area, except for a top layer of clay, consisted mostly of sandy soil. The excavation was hampered by the emergence of a large amount of groundwater, affecting the progress of the project. Therefore, well point dewatering was adopted around the perimeter of the dry dock to solve this issue. To rapidly lower the water level, well points were installed around the dry dock in sections. The well point system is the best dewatering method in ground improvement projects. Once the groundwater was removed, the originally wet and soft ground became dry and solid, making construction easier. Moreover, as the excavation of the dock proceeded deeper, the water level could be lowered layer by layer, greatly benefiting the foundation excavation and construction of structures. Due to the effective well point construction method, excavation progressed very smoothly, reaching a peak with a single-month record of excavating 330,000 cubic meters, totaling 1.46 million cubic meters excavated. The second area, being a fish pond region with thick silt and parts extending into the sea, employed a combination of dredging and dry excavation methods. The RSEA construction personnel quickly completed the dredging operations near the dock entrance within just 53 working days using dredgers. Subsequently, the outer perimeter of the dock entrance was sealed, and a temporary cofferdam was constructed. The cofferdam is essential for the future construction of the entire dockyard, which could only be removed upon completion. Once heavy machinery reached an elevation of -10.3 meters, foundation treatment began. To effectively prevent groundwater infiltration, U-shaped steel sheet piling was driven around the perimeter of the dockyard, including the lock gates and the main and auxiliary pump chambers, reducing the original seepage rate of up to 250 cubic meters per hour by half. Vibration-driven sand piles were then used to improve the soft soil, increasing soil density and enhancing load-bearing capacity. Apart from the dock wall foundation and the central base plate, this type of sand pile was used throughout the dockyard. Coarse sand was chosen for the sand piles, which were vibrated into the designated strata with steel tubes to enhance load-bearing capacity and reduce excessive groundwater concentration. Each sand pile measured 10 meters in length, with a total of over 17,000 piles driven, using 57,000 cubic meters of sand. The dockyard foundation utilized pre-stressed concrete piles for support, with more than 10,900 piles driven, ensuring a very solid foundation for the dockyard. Finally, cutting off the heads of the completed pre-stressed piles above the design line marked the completion of an important step before starting the superstructure engineering. The dock wall construction extended from the dock head wall towards both cantilevers, connecting the rebar on the pile heads with the dock wall foundation, with each dock wall foundation concrete segment ranging from 250 to 300 cubic meters. After completing the dock wall foundation, the first layer of rebar tying commenced, utilizing a comprehensive modular steel pipe scaffolding system for safety, durability, and convenience. The introduction of standard modular steel forms allowed for the assembly of each layer of the dock wall, one segment at a time, using just 20 large steel forms, saving significant time. To align with the construction schedule and improve efficiency, high-performance concrete pump trucks were chosen for all machinery aspects to carry out concrete pouring. In addition to the wall surface, floating walls were constructed every 5 meters behind the dock wall for support. After completing the first layer, construction advanced to the second layer. Thanks to the introduction of new equipment and methods, the dry dock's main body construction progressed very smoothly, achieving high construction quality. The dry dock wall structure was divided into 96 segments. The pouring of each concrete segment, from the foundation to the second layer, carried out in 3 stages, requiring 288 concrete placements in total. To effectively manage the progress of the dry dock wall construction, the RSEA employees, demonstrating their inherent team spirit, worked tirelessly through the rainy season. As each dock wall segment was completed, to prevent displacement from soil pressure during backfilling, construction of the 2 side base plates at the dock bottom was synchronized. The base plate design followed the principle of elastic plates, featuring a decompression drainage system to eliminate the uplift force of groundwater on the dock bottom. Concrete placement for the base plates was divided into 196 segments, each requiring 450 to 600 cubic meters of concrete, often achieving a record of 1,000 cubic meters of concrete placed in a day. Backfilling operations behind the dock wall involved adding a layer every 30 centimeters, compacting it to the design density before continuing to layer up. After backfilling, a working corridor was built along the perimeter at the top of the dock wall, facilitating the smooth installation of various equipment used in shipbuilding operations. The foundation for the middle gate set in the central section of the dry dock includes 6 guide slots and support seats, all of which are made from high-strength concrete structures. The construction of the crane foundations on both sides of the dock, which are required to support weights exceeding 3,500 tons, demands meticulous attention to detail. The crane's track uses steel rails weighing 100 kilograms per meter, making it the heaviest per unit weight track in the country. After completing the front section of the dock, it was handed over to the China Shipbuilding Corporation for the assembly of a 350-ton giant crane. This giant crane spanned a million-ton dock, with a reach of 177 meters and a height of 87 meters, the crane body alone weighing over 3,000 tons. During pile driving, the massive crane body's main beam was lifted to the installation position at a very slow speed. The giant crane, one of the main pieces of equipment for shipbuilding, was installed in 2 units, becoming a significant symbol for the China Shipbuilding Corporation. Mr. Chang Qingque, the premier at the time, showed great concern for the construction of the large shipyard and made multiple visits to the construction site, praising the progress of the project and the hard work of the RSEA employees. The wharf project, one of the ancillary facilities of the shipyard construction, involved driving C-shaped steel sheet piles with a total length of 1,088 meters to delineate 3 wharfs, numbered 2, 3, and 4, each with a water depth of 10 meters. To prevent displacement or deformation of the steel sheet piles, anchor walls were installed on the inside of the wharfs, connected with high-tensile steel cables. Due to tidal effects, operations had to be carried out 2.5 meters below sea level. Concrete foundation piles were driven on the wharf surface to support 20-ton gantry cranes, and concrete caps were poured over the steel sheet piles to protect the wharf embankments. The entire project for Wharf 2 was completed ahead of schedule in February 1975. The dry dock featured 9 underground substations, located beneath the foundations on both sides, with the mid-section's water inlet channel extending from the collection chamber to the sea surface at the dock entrance, spanning 140 meters in length. This allowed for sectional pumping and draining post-completion, with additional pipes laid for standard drainage systems. The main pump room, located on the outside of the right cantilever at the dock entrance, reached a foundation depth of -17.5 meters below ground level, marking the deepest foundation among all structures. The pump room, standing 20.5 meters tall, due to its complex structure and the coordination of various embedded object constructions. Therefore, from the installation of foundation piles, excavation, to the completion of concrete pouring, required round-the-clock operations. The auxiliary pump room, located outside the left cantilever wall of the dock entrance, was equipped with 1-meter diameter inlet pipes to assist the main pump room's operations and could also serve as a midsection inlet chamber. After completing the main pump room, installation of 3 2-meter diameter pumps began, each capable of pumping 40,000 tons per hour. Using all 3 pumps simultaneously, approximately 900,000 tons of water could be extracted from the dock in just 7.5 hours. The main gate's foundation construction involved driving 240 pre-stressed concrete piles, as the foundation had to support a main gate weighing over 8,000 tons, necessitating strict construction requirements. The second phase of the dry dock project was handed over to the owner in June 1975, and on November 18 of the same year, construction of a 445,000-ton mega cruise ship began, with a keel-laying ceremony held inside the dock. Thus, the shipyard and ship construction proceeded side by side, with the concrete structure of the dockyard nearing completion. Over 21 months of work, a total of 235,000 cubic meters of concrete was poured, with the last section of the dock space slab completed on the evening of December 26, 1975, celebrated enthusiastically by everyone involved. The foundation work for the main gate had already been completed, but the installation of the gate could only proceed after the overall structure was finished. The floating-type main gate, installed at the dock entrance, was 14 meters high, 92 meters long, and 6 meters wide at the top, serving not only as a water barrier but also as a passageway between the left and right cantilevers, weighing over 8,000 tons in total. The completed main gate underwent a week of pressure testing, proving its water-blocking function to be very effective and in accordance with design standards. At this point, the temporary cofferdam outside the gate was to be removed, using dredging to clear the mud and silt from the cofferdam and to continue deepening the channel in the dock mouth area. Finally, the middle gate was installed on the guide slots and support seats in the central section, allowing the dry dock to be used in sections according to the actual needs of shipbuilding. Under the continuous efforts of the RSEA employees, working day and night, rain or shine, the China Shipbuilding Corporation Kaohsiung Main Plant Engineering completed the million-tonne dry dock project on June 8, 1976, fully demonstrating the RSEA employees' traditional spirit of fearlessness towards hardship and difficulty. The entire construction project took only 29 months, completing 3 months ahead of the scheduled timeline, becoming the earliest completed and first operational project among the government's 10 major construction projects. This modern-equipped large shipyard, with an annual shipbuilding capacity of 1.5 million deadweight tons and a ship repair capacity of 2.5 million deadweight tons, was one of the largest shipyards in the world at the time. The completion of the large shipyard not only propelled our country's shipbuilding industry into a new era but also established a good reputation internationally, making every Chinese proud. The first vessel, the 445,000-ton giant cruise ship the Burma Endeavour, commissioned by the American Gatex Oswego Corporation, held its naming and launching ceremony on June 3, 1977, attracting tens of thousands of people from home and abroad to witness its splendor and leaving a profound and tangible impression on the achievements of the country's major constructions. The RSEA's veteran employees, drawing on their past experience and confidence in this project, not only demonstrated the excellence of our country's engineering and construction talents but also significantly enhanced the nation's central strength, making it greater and more powerful. Today, the former China Shipbuilding Corporation has transformed into the CSBC Corporation of Taiwan. The ships constructed at the factory are primarily commercial vessels, such as container ships or carriers, gas transport ships, coal ships, and a few dredgers and other workboats. It is also in line with the government's development of offshore wind resources, preparing to manufacture workboats for offshore engineering, aiming to make Taiwan a hub for offshore wind power in Asia. It is hoped that this large shipyard, built on the sacrifices and dedication of the RSEA workers, will continue to strive for excellence in the future, delivering outstanding results once again, navigating the world and heading towards the future.